Hello everyone. I'm recording the tutorial for MAT102 to accommodate those who cannot come to in-person tutorial because they have to be in quarantine. However, I'm not sure that I will keep recording it after February, so please try to come to class if you can. I actually went over everything and I pressed share screen, but then I forgot to press record. That's why you see there's already something here. I didn't want to erase, so I will just talk about it. This tutorial will cover chapter 3.1 up until 3.5. When we were in class, I said it covered up to 3.4, but then I realized I talked about negation as well. That's why 3.5 is included in here. So chapter 3 is about informal logic. And the first thing we have to know is definition of mathematical statement. When does a sentence become mathematical statement? So you can tell whether it is a math statement or not by checking whether it has the truth value, whether you can categorize the sentence as true or false. If you can, that is a math statement. If you cannot, that is not a math statement. For example, I like ice cream. That is not a math statement because we don't know who is I and we cannot tell whether it is true or false. Also, x is greater than 9. We don't know what is x, so we cannot conclude it is greater than 9 or no. However, if you say for every x real number, for every real number x is greater than 9, that is false, right? Because there exists real number that is smaller than or equal to 9. So when you can categorize it as false, then it is a math statement. For a sentence like x is greater than 9, we call it a predicate. A predicate is a sentence that can possibly turn into a math statement by assigning value to it. For example, if x equals 10, then x is greater than 9. We can assign a value to variable x to make it become a math statement. Or we can use quantifier for every x in R or quantifier there exists. So predicate can be turned into math statement by using quantifiers or assigning specific value. Then we have to remember that predicate doesn't have quantifiers. Why? Because if a predicate has quantifiers in it, it becomes a statement already. It's not a predicate anymore. So the predicate itself doesn't have any quantifiers. I saw this mistake in upper year student as well, not just in Math 102. So I hope that you can remember it and not repeat the mistake. Second mistake is people say, if x equals 10, for every x in R, x is greater than 9 is true. This is wrong argument. Why? Because you can assign value to the predicate in order to give it truth value. However, this one for every real number x is greater than R, so x is greater than 9, is already a math statement itself and it has its own truth value. So even when you assign specific value for the variable x, it doesn't change the truth value of this statement here. So the statement here is false because not every real number is greater than 9. So the argument here saying like this is false, and you shouldn't do that. You can say if x equals 10, x greater than 9. That is good because x greater than 9 is a predicate. And you can assign specific value when it is a predicate, but you cannot assign specific value to change the statement's truth value. So this one is like independent statement, so it has its own truth value. It doesn't depend on the input here. So this argument is wrong. Okay, so next we will talk about the logic that we come across in chapter 3. First, we have and. The logic and is true only when both of the statements are true. So when P is true and Q is true, then P and Q is true. That is the only way. If any of P and Q is false, then the P and Q will be false. You can check its truth table either online or in the course note. P or Q. This logic is true when at least one of P or Q is true. So either P is true or Q is true, or both of them are true. Then the logic R will be true. Next is P implies Q. So when we have true implies false, the implication is false. When we have true implies true, the implication is true. And the last two is a bit abnormal. Like when we have the if condition is false, then no matter what is Q, P implies Q is always true. And we call this one vacuously true. Because why is it vacuously true? Because if you just have any statement as an example, is like if there is a unicorn, then I will not like cats. Like the if statement already is not true, so you cannot really tell the truth value of the implication. It's not very intuitive. However, if you think about the negation of implication, we have negation of P implies Q equal to P and not Q. And when P is false, then P and something is always false, right? Because the logic and need both of them to be true, but we already have one statement is false. So the logic and here is false, which means the negation of P implies Q is false, which means P implies Q is true when P is false. Okay, I hope that makes sense. If not, you can feel free to ask on Piazza or email me or come to TA or professor's office hour. Next thing is the logic P if Q and Q if P. This is called if and only if. It just means P implies Q and Q implies P. So this one is true if and only if both of them are true. And both of them are true when P and Q are both true or both false. You can try drawing the truth table for this and you will see. Let's move to the first question. You can pause here 3 to 5 minutes to think about it because thinking process is really important in this course. Obviously, knowing the answer helps, but it doesn't help that much if you don't think. So we have a statement R for all real number X. If this, then this. And we want to see if this statement is true or false. And remember, like the implication here has to be true for all real number X in order for the statement to be true. So we will first write R using logic symbol. We have for all, which is the symbol here. Real number X means X is in R. We have X minus 1 times X minus 3 equal 3. If then is an implication relationship. If P then Q means P implies Q. So we have this, then X minus 1 equals 3 or X minus 3 equals 3. Okay. So these are using the logic symbol. And when we think about is our true or false, so if I'm in the test, I will not care about the value that doesn't satisfy this, because obviously those value that doesn't satisfy this, the implication is true because this one is false. So we don't care, and we also don't have to mention it. We just need to care about x such that x minus 1 times x minus 3 equal to 3. So I will say 5 or x such that x minus 1 times x minus 3 equal to 3. Then I expand it out. I have x squared minus 4x plus 3 equal to 3. Give me x squared minus 4x equal to 0. And that give me x times x minus 4 equal to 0. So x equals 0 or x equal 4. Okay, so for a problem like this, when you already found the x that satisfy if statement, you will plug those value of x into then statement to see like if that x satisfy the if statement and it doesn't satisfy the then statement, which means the whole implication is false. Okay, and if you check for all values of x that you found here, and the implication is always true, which means the statement is true for all real number x. So we will try with x equals 0, then x minus 1 times x minus 3 equal to 3 is true. When x equals 0, x minus 1 equal negative 1, which is different from 3, and x minus 3 equal negative 3, which is different from 3. So x minus 1 or x minus 3, so x minus 1 equal to 3 or x minus 3 equal to 3 is false. So when x equal to 0, the if is true. So P is true and Q is false. So we have the implication true implies false, which is false. So we have false. And when x equals 0, the predicate here is false, which means it is not true for all real number x. Therefore, the statement R is false. Yeah, I say false here. Okay. Move on to question 2. Please again pause 3 to 5 minutes to think, or maybe more, it's just up to you. So for question 2, the first thing we have for every integer x, there is like for every integer x, there is always a natural number such that x is divisible by that natural number. Why do I know that? Because x divide y equal to an integer means that x is divisible by y. What does divisible mean? It means 4 is divisible by 2 because 4 divided by 2 is an integer. 9 is divisible by 3, but 7 is not divisible by 3. Things like that. And it's claiming that for all integer x, there is always an y such that, a natural y such that it is true. This statement is false. We can pick counter example as x equal 1. Then 1 over y is an integer. If and only if y is 1. So either either 1 over y is not an integer, or y have to be equal to 1. So x equal 1 disprove this statement. You can think about its negation, which say exists x in Z, because negation for every is exists, right? for negation of there exists is for every y in N, x equal y is not an integer, or y is 1, which means there is an x such that x over y is not an integer unless y equal to 1. Then this one here prove this statement, which means it proves the negation of the original statement, which means it disproves the original statement. So this one is false. For the second statement, they say there exists an integer x such that for all natural number y, x over y is an integer and x is not 0. So it's just saying there is an integer such that it is divisible by all natural number, and that integer is not 0. When I think about an integer that is divisible by all natural number, the only possible number that can do that is 0. But we have condition x is not 0 here. So if we exclude 0, there is no number like that. So this one is false because 0 is the only integer divisible by all numbers, all natural number. So, okay. So this is the explanation that I have. However, if you cannot think of this argument, you will have to prove the negation of this one is true. And normally, I know that some of you may heard that in order to disprove something, you just need to find one counterexample. But it is not totally true. So for a statement like this, for all number x, blah, 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 then one counterexample can disprove it. Why? Because it is the same as I'm saying that everyone in the classroom likes cats. You can disprove me by giving me one person in the classroom who doesn't like cat. It makes sense, right? However, if I say there exists, like there is a student in the class who like cat, and you give me your friend in the class who doesn't like cat, then it doesn't disprove me at all, because let's say the class have 26 students. I just need one person in the class to like cat in order to prove my statement, right? Because I say there is someone in the class who like cat. And in this case, in order to prove, I just need one example. However, in order to disprove me, you have to check that everyone in the class, check each of them, everyone in the class, and they all don't like that. Then in that case, my statement is wrong. But if you just give me the friend sitting next to you who doesn't like that, then it doesn't disprove me at all, because 25 other students, there might be someone who like cats in there. Okay, let's move to question 3. Again, please pause if you want to, and I recommend you to do that. Question 3, so basically here it is a student's answer. Like I kind of fake the student answer, but I use their logic when they answer some similar kind of question, because I want to show you what is the problem with the logic here. So the statement they have to consider is, for every real number x is negative implies for every real number x is odd. And they say that if you take x equal -10, then for all real number x is negative is true because -10 is a negative number. And when x is equal to -10, x is odd, is false because -10 is an even number. Therefore, we have true implies false is false. What's wrong in this way of argument is they are assigning value x equal -10 to a statement. This one here, it is the statement itself. It has its own truth value, right? So its truth value doesn't depend on when x equal to -10. So the truth value of this is false because every real number is negative. It's a false claim because they are positive or also zero as well. They are all real numbers. So the statement here is false. And of course, this statement is also false because not every real number is an odd number. So the implication here should be true, and it is vacuously true. What's wrong in this argument? Again, I want to emphasize that you cannot pick a specific value of x, then put it to the statement to change its truth value at all. You can say x equal -10, x is negative. That is totally correct because x is negative is a predicate. And in that way, when it is a predicate, you can assign a specific value to determine whether it is true or false. But this one is a statement by itself already. You cannot do this. Okay. So the student answer is false. The student answer is wrong. Let's look at 4. So when they ask you to prove two statements, they are logically equivalent or not, just draw the truth table. So you have P, Q, not Q, then not implies, PR, not Q, okay? So you have two statements here, and each statement has the possibilities of being true or false. So each statement has two choices for its truth value. So P have two choices, Q have two choices. So in total, you have 4 possibilities, which means you will have 4 rows here for the truth value. If you have a third statement called R, then you will have 2 times 2 times 2, which is 8 possibilities. So if you have a new statement here, which is R, you will need 8 rows here. If you have 4 statements like R2, you will have 16 rows here. So in general, you have 2 to the power of n possibilities, where n is the number of statements that you have. Okay. So back to our example, we have 4 choices here, which is true, true, false, false. So when P is true, Q can be true or false. When P is false, Q can be true or false. Not Q will be flipped value of Q, which is false, true, false, true. So this column is a negation of this column. So negation of true is false, negation of false is true. And for the last column, we just need to see value of P and not Q. We don't really care about this column anymore. So we will look true or false is true. True or true is true, false or false is false, or false or true is true. Okay. And when you draw the second table, I recommend you to bring the exact order of input here down below. So that in the last step, you just need to see whether the two last columns are exactly similar. If you don't put the correct order here, maybe you have false true here, then when you compare two tables, you will have to look, when we have false true here, the answer is this. Then you have to look false true here, the answer is this. You cannot automatically just look at the last column anymore. That's why I recommend bringing this down. So we have true, 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 false, false, true, false, false. And we have statement not P, not Q, not P implies not Q. Okay. So not P is flipped value of the first column, not Q is flipped value of the second column. So I have false, false, true, true, false, true, false, true. And not P implies not Q. We use result from these two. Not P implies not Q. False implies false is true. False implies true is true. True implies false is false. True implies true is true. So we look at here, the last column are exactly similar. So we can say, so they are logically equivalent. Okay. So let's move to question 5. Again, you can pause and think about this question. You can draw a truth table. It is not wrong, but I would say it is not the most efficient solution to do here. So please think about that. I will start solving this. If the statement not P and not Q implies R is false, then what is the truth value of PQ? So we have A implies B is false. There's only one way to make the implication false, right? Because if you look at the implication truth table, there are 3 rows of true and 1 row of false. And when the implication is false, it is when A is true and P is false. Okay. So here, this one here is A, this one here is B. So we have not P and not Q implies R is false when not P and not Q is true and R is false. We don't really care about R here because they didn't ask for that. We just care about value of P and Q. So here we have not P and not Q is true. We have A and B is true only when A is true and B is true. So not P and not Q is true only when not P is true and not Q is true. So not P is true when P is false. Not Q is true when Q is false. Okay. So the answer for truth value of P and Q is false and false. For the last question, I left this as an exercise for in class for people who join in-person tutorial because I didn't have time to go over it. But I guess I can solve it now for you as well. So same as the first question, I start to find x such that absolute value of x minus 1 is less than or equal to 2 and x in Z is true, which means this one is equivalent to find all integers x such that x minus 1 is less than or equal to 2. So you have absolute value of A is less than or equal to B if and only if negative a less than or equal to a less than or equal to negative b. Okay. And let's say if you have negative absolute value of a is greater than or equal to b, which means a is greater than or equal to b, or negative a is less than or equal to negative b. So here we use the property here. So we have absolute value of x minus 1 is less than or equal to 2, which means negative 2 less than or equal to x minus 1 less than or equal to 2, which means, sorry, x squared, is it? No, it is x. So we have plus 1 to every side. We have negative 1 less than or equal to x and less than or equal to 3. So here we have x squared. So let's look at this. A real number line, you have negative 1, you have 0, you have 1, 2, 3. And if you have x squared, this one will be 1, this one will be 0, 1, 4, and 9. And you can see that for x in this range, this one is x, this one is x squared, then x squared is in this range. And the minimum value is 0 because x squared is greater than or equal to 0. It is a basic fact, so the minimum value is 0. And the maximum value it can achieve is 9. It is when x equal to 3, right? So from here we can have 0 less than or equal to x squared less than or equal to 9. Okay, because in here we want all integer. So we have x is in negative 1, 0, 1, 2, and 3, right? Because they are all the integer that is in this interval. And if you square each of them, you will have 1, 0, 1, 4, and 9. And minimum is 0, maximum is 9. So that's why I know this. And then we have x squared minus 1. So I minus 1 to all three sides. So we have 0 less than, sorry, minus 1 less than or equal to x squared minus 1 less than or equal to 9 minus 1. And this gives me negative 1 less than or equal to x squared minus 1 less than or equal to 8. Okay, you can see here, this one is negative 1 and 9, this one is negative 1 and 8. You might think that the claim here is false. However, that is not all. We have negative 1 less than or equal to x squared minus 1 less than or equal to 8. And 8 is less than or equal to 9. 8 less than or equal to 9 is true statement because 8 is actually less than 9 and this one is less than or equal to. So just need one of those possibilities to make it become true. And there's a basic fact, a less than or equal to b, b less than or equal to c, then a less than or equal to c. So we use it here, negative 1 less than or equal to x minus 1 less than or equal to 9. It is true. And the thing here is true for all the value of x that we found in here. So the Q part is true for all the value of x that satisfy the P part. Therefore, the statement R is true. So this one is true. Okay. And if you write a logic symbol, let me copy it down. Let's see. I will negate each part. So first part, for every x in R will be x is x in R. Here we have the implication P implies Q. In negation, it will become P and not Q, right? So I will keep the P part similar. I don't do anything, but I will negate the Q part. So I bring the P part down exactly the same And instead of imply, it is all, sorry, it is n and then not q. So negative 1 less than or equal to x squared minus 1 less than or equal to 9 means negative 1 less than or equal to x squared minus 1 and x squared minus 1 is less than or equal to 9. And then we want the negation of it. So negation of a and b is negation of a or negation of b, which means negation of this part, which means negative 1 greater than x squared minus 1, or negation of this part, x squared minus 1 greater than 9. So here I will have negative 1 greater than x squared minus 1, or x squared minus 1 greater than 9. Okay, so this one is the negation that we have to find. Okay, thank you everyone, and please feel free to stop by office hour of any professors or TA if you have any question. Thank you.